Hello everybody, hope things are going well for you today. It's going to be a great stream today. Sorry for starting late. So here's what happened. Okay, so I get started, or I'm about to get started. I'm getting my computer ready, and I get a notification that says I need to restart my computer because some app needs to update. And so I restart my computer, and it turns off, and then it says 45 minutes is the estimated wait time. Well, fortunately, it was only 20 minutes in the end, but anyway, so that's what happened. But I'm here now, and so we can do our regularly scheduled stream, which includes the topic of nuclear physics, which of course is everybody's second favorite topic after exoplanets. All right, here we go. Start with some astronomy picture of the day. We are in September. We can probably make it up to the solstice. How about if we go up to the solstice? The Crab Nebula from the VLT. This is a very famous image of the Crab Nebula in Taurus. I didn't realize it was in Taurus. Well, now we know. There we go. That is the Crab Nebula, a supernova explosion from 1054 AD. Globular cluster M3. Now that is a pretty globular cluster from Captain, or what's Honeycutt? BJ Honeycutt? BJ Honeycutt from Indiana University on WIN. WIN is Wisconsin, Indiana, Yale, something observatory. All right, Hurricane Isabel approaches. That is what a hurricane looks like in all of its power and glory from the top. And of course, it is spiraling in the counterclockwise direction, which is what you would expect. In the northern hemisphere is what you'd expect. 2-mass galaxy sky. Whoa, that's cool. So that is what galaxies look like in the 2-mass data. Again, 2-mass is the 2-micron all-sky survey. Let me get a little bit more light on my face so that I look even more prettier than I normally do. All right, 2-mass all-sky survey. All those dots are galaxies. Hurricane, we did that one. Saturn by 3. 3 different images of Saturn. It's reached its maximum 27-degree tilt towards the Earth. Okay, there we go. That is what Saturn looks like. Giant storms comparable to the size of the Earth have been erupting in Saturn's cloud tops. Like volcanoes, except there aren't as many houses. And for some reason, these links are not updating. Okay, there we go. Now they're updating. Galileo's Europa. That is what Europa looks like from the Galileo spacecraft, which is no longer. Galileo is now dead. Anyway, so there we go. That is what it looks like on the surface of Europa. Apollo 11 catching some sun. Lots of sun. This is where they're planting the, whatever that is, the pièce de résistance. Apollo 11, image of the lunar surface taken by Apollo 11. Neil Armstrong, the first to walk on the moon, pictured is the mission's lunar module, the Eagle, and spacesuited lunar module pilot Buzz Aldrin, unfurling a long sheet of foil known as the solar wind collector. The surface of Uranus is not quite the same. It's a little bit more squishy. Exposing the face, the foil traps atoms streaming outward in the solar wind, ultimately catching a sample of material from the sun. Along with moon rocks and lunar soil samples, the wind collector was returned for analysis in earthbound observatories. What else we got? Apollo, we did that one. Inside the Eagle Nebula. Inside the Eagle Nebula. So the Eagle Nebula, the pillars of creation, the Hubble image, is this portion right here. That portion with these 3 little pillars that are sticking up. The rest of this cloud is just part of the greater Eagle Nebula. And you can see that it's being hollowed out by the presence of the young stars that are forming in that area, in that environment. All right, that takes us to the end of this, and that is the autumn. Oh, actually, the solstice in the equinox. The equinox is the 23rd of September, so we have a couple more. There's no way there's not other forms of life out there. I think that most people believe that there probably are other forms of life out there. Right now, there's no evidence for it, but that doesn't mean it's not there. Opportunity rockets. Opportunity rockets towards Mars. This is the Opportunity rover, the second half of the Spirit rover opportunity, or the Spirit rover and Opportunity rover tag team missions. Okay, cover as much as 40 meters per day. 40 meters per day, as opposed to this Sojourner rover, which was tiny, that would do like a meter a day. They will search for evidence of ancient Martian water and the implications about the possibility of ancient Martian life. All right, last one, egging on the autumnal equinox. So this is people standing eggs on their end, and the fact is you can stand eggs on their end all the time, not just on the equinox. Pictured above, fill plate acted as a bad astronomer, balancing 3 roc's eggs on the end in late October, which is not the equinox. If they did it in late October, his wife balanced 5 more. The little appreciated fact that most eggshells have small bumps on them makes them seemingly impossible for the task achieved. During an equinox, every place on the Earth experiences equal amount of day and equal amount of night, but it doesn't affect the gravity of the Earth or anything like that. So there we go. That just shows that not to believe everything you read on the internet. Only believe the things that you see on Twitch. Hold on. And even then, certain Twitch channels. All right, let's see. What do we got going on? So today we will be doing nuclear physics. So we need to pull up a good nuclear physics background. What would be a good nuclear physics background? Like cooling towers, nuclear power plant. Images. Need a really cool cooling tower so we can... That's what we want. We want this kind of cooling tower. Look at that beautiful cooling tower in the background. It's a perfect backdrop for our discussion about nuclear. Will we be making bombs today? I think maybe bombs today, and then nuclear energy. So nuclear energy will be a later discussion. I don't know if we'll get to it today. So today it's mostly just nuclear physics. So I need to switch real quick to a different screen, and then we can get started. All right. So today's plan, nuclear physics. Not necessarily nuclear energy, but we will probably get to some nuclear energy at some point, but nuclear physics is the main topic. What do we got going on? We got radioactivity, we got radiation detection and detectors, substructure of the nucleus, nuclear decay and conservation laws. Okay, so no problem. Half-life and activity, binding energy and tunneling. Okay, sounds good. When do we get nuclear weapons, fission, fusion? Okay, so this is just nuclear decay and radioactivity. Okay, well, fair enough. And then we'll get to how to destroy people later. All right, here we go. Nuclear physics. So I guess this is not really the appropriate background to have for our nuclear physics, but we're going to do it anyways. So in the nucleus, there are a number of forces that are acting. 2 in particular, well, 3 that matter. Gravity is not very important in nuclear physics, but it is important in the grand scheme of things. But in the local scheme of things with nuclear physics, the important forces are the strong nuclear force, the weak nuclear force. These are both nuclear with a C, nuke, and then electromagnetism. Now, the reason electromagnetism is important is because of the way that it relates to the weak nuclear force. the strong nuclear force is the force that binds the nucleus together. The thing that binds in the nucleus, we have, so each, let's go back to this from what we started a couple months ago. Each of these forces has a charge associated with it, or a type of charge associated with it. With the electromagnetic force, it's called the electric charge. It has two varieties, plus and minus. With the strong nuclear force, there are three charges. They are red, green, and blue. Actually, I guess I think I mentioned this last time. With the electromagnetic force, it's actually one charge. It's the electric charge, and that charge has two different. That charge is signed. It's either positive or negative. With the strong nuclear force, there are three charges, and these three charges also have signs, and so you can get red, anti-green, and anti-blue. So there's only one electric charge that can have either a positive or negative sign. There are three color charges that can have positive or negative signs, and they would look like that would be these 6 different particles. Okay, so the strong nuclear force. It is the interaction of these different charges, the strong nuclear charges, with the particles that are exchanged in those forces. With those forces, those are gluons, where with the electromagnetic force, it's the photon. So the electromagnetic force has a photon that mediates the force associated with these charges. The strong nuclear force also has particles that are exchanged in these kinds of interactions, and those are called gluons, and they couple to these charges, the red, green, and blue charges. So in the nucleus, you basically will have 3 quarks, and I mentioned this before, that you need to make color neutral particles. We don't see color charge out in the open, so everything that is produced comes in color neutral packages, whether it's a color and an anti-color, or whether it is 3 colors. So if you have red, green, and blue, you have 3 quarks, red, green, and blue, and these are going to exchange gluons. The chemical symbol for gluon is a spiral thing like this, kind of like an inductor for electromagnetism. Anyway, so these gluons are exchanged back and forth between the red, green, and blue quarks in the nucleus, or in your particles, not necessarily the nucleus, but this could be like a proton. So as these things are exchanged, one thing that's important to note is that, like this one here, for example, the actual diagram would look something like this. You have a quark coming in, and it's going to be like a red quark, and it's going to come out as a green quark. And then over here, you're going to have let's say a green quark here and a red quark there. And so what you're going to end up with is something that looks like, here's your gluon, connects there, and this would be like a red anti-green. Red, with an R. Here we go. Come on, you can do it. There we go. Red anti-green. Okay, so it's red anti-green, so that the redness of this quark persists through here. It's conserved. The charge is conserved, similar to electromagnetism, how the electric charge is conserved. So the red is conserved through this, and then here is the red right there that comes out this way. So the red goes in this way, goes across this interaction with this red-green gluon. So the gluon has 2 colors associated with it. And then this one here, you have a green coming out this way. If time is in the vertical direction, you have a green coming out this way. Let's see, does that work? Is this right? If I'm going up, so you have green going this way, you have anti-green, so there was no green coming in, there's no green coming in, and so you have to have anti-green going this way. Yeah, okay, so here's anti-green moving in this direction, and then that means that this green quark, so this green quark is here, it comes along, here's the interaction that they both share. You have a green quark coming in, and it needs to annihilate into anti-green. So green comes into this vertex with anti-green, red comes into this vertex and produces red. And so the green changes to a red, and this red changes to a green by emitting a red and absorbing an anti-green. It's actually probably, I suspect that it's actually a combination of red green bar plus red bar green, 1 over root 2. That's probably what this looks like. Let's take a look at this and see what it actually looks like in the details. So what are the different gluon types? Different gluon colors. There are 8 of them, 8 gluons. Where are they listed? That is not helpful. Color charge. Let's see what if the gluons are in here. Gluon. Gluons have a combination of two color charges, one of red, green, and blue, and one of anti-red, anti-green, or anti-blue, in a superposition of states that are given by the Gelman matrices. All other particles have zero color charge, mathematically speaking. The color charge of a particle is the value of a certain Kortic-Casimir operator in the representation of the particle. So let's see if they have a table of... nope, they do not have it. So anyways, but that's... see what these gluons look like, if they can have one in here. So you get... this may be difficult to understand intuitively. Quarks carry three types of color charge. Antiquarks carry three types of anticolor. Gluons may be thought of as carrying both color and anticolor. This gives them nine possible combinations of color and anticolor. However, one of those degrees of freedom is removed, and so you actually only get 8 gluons instead of 9. The combinations are here: red, anti-red, green, anti-green, red, anti-blue, green, anti-red, blah, 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 etc., and so forth. These are not the actual color states of observed gluons, but in fact, rather effective states. To correctly understand how they are combined, it is necessary to consider the mathematics of color charge in more detail. Okay, here's a color singlet state: red, anti-red, blue, anti-blue, green, anti-green, over root 3. And gives you these 8 colors. Oh, there we go. That's the one that I just mentioned right here. 8 remaining independent color states, which correspond to the 8 types of 8-color gluons. Okay, so this color singlet states, all right, what does this mean? In other words, if one could measure the color of the state, there would be equal probabilities of all of these things. So this is a color singlet state, and that one doesn't count. This one doesn't actually contribute to the gluons. The remaining 8 is this combination here. And so my guess is that the one that I just showed you would correspond to a gluon that looks like this: red, I see it'd be red, anti-green, green, something like this. And that corresponds to this exchange that's right here, where the gluon carries some of these colors with it, and it facilitates this exchange between a red gluon and a green gluon, for example. All right, let's see. Here's a question. Are these verifiable laws, or are they just theories at the moment? Are they actually colored? So they're not colored in the same way of like they actually have some physical color, like it's a blue pigment, because these are like a blue pigment is going to be a fairly large and complex molecule. These are subatomic particles that have a charge associated with them, and we had to come up with a name for those charges that would make some kind of intuitive sense, and color is the name that we chose. So these are actually verifiable laws. We can tell that that quarks exist. That's what it basically boils down to, is do quarks exist? And yes, quarks do exist. We can see them, we know that gluons exist, and we understand the way that the theory describes the behavior of the quarks and the gluons matches the observations of what we see in the quarks and the gluons. Anyway, so this is the kind of exchange that you'll happen. You'll have a gluon exchanged over here. This gluon's going to have some combination of color charges associated with it as well, and then that will facilitate these kinds of interactions. Now, something that's notable here is that you will see this gluon, it's going to have this combination. The gluon carries color charge. The gluon carries the charge with it. Photons have no electric charge. So when you have two things interacting with photons, say you have like an electron here, an electron there, when you have things interacting with photons, it's got a different chemical symbol. It's just a wiggly line instead of a loopy line. Photons don't carry the charge along with them, which means that if you have a lot of photons in the field, there's still no color charge associated with it. So you have like an electric field, but you don't have electric charge. When you have an intense gluon field, you actually get the gluon charge. You get the color charge along with it. And so as a consequence, the gluon field can interact more readily with itself than the photon field does. It's coupling to its own color charges. And so this produces, one of the things that this produces is called asymptotic freedom and confinement. I can't remember exactly what all the details are of these things, but nevertheless, the moral of the story is that if you take two quarks like this, so here's one quark and here's another quark, these quarks have color charge associated with them, green and blue or something like this. As you pull these quarks apart, the strength of the coupling gets stronger as they're pulled apart, or the energy in the field gets stronger as they're pulled apart, to the point where you eventually cross a threshold, E equals mc squared. It's actually going to be E equals 2 mc squared, where you can spontaneously produce particles out of the gluon field. So the gluon field will spontaneously produce a pair of particles. This won't happen with the electromagnetic force, because the electromagnetic force gets weaker as you pull these things apart, because you're not generating any new charge in between them. So if you take two electrons and you pull them apart, the force between them gets weaker. If you take two gluons and you try to pull them apart, the force between them gets stronger, because the gluon field that's connecting the two also carries that same color charge. And eventually what happens is you will spontaneously produce a quark anti-quark pair. The quark will go on one side, the anti-quark will go on the other, and you'll produce a meson and a particle that you had with. So I mentioned this before, like a proton has 3 quarks in it, and then you'll produce a pion out here that has a quark anti-quark pair. So this would be a quark anti-quark pair, and that comes from this spontaneous production of a quark anti-quark pair out of the gluon field, because the energy in the field grows as you pull things apart. So that's cool. That tells you, well, there you go. There's nuclear physics, all in a nutshell. Any questions on nuclear physics? All right, what else is going on here? Well, when you have a nucleus, so the nucleus is bound together by these fundamental forces. You have a bunch of particles that are attracted to each other through these gluon fields. And if you look at the potential for the combination of the strong nuclear force and the electromagnetic force, actually, if we just look at the potential for the strong nuclear force, it looks like this. It actually dies off. So it's very deep, like this, and then it probably gets weaker like that. Okay, so it does die off with some distance. This is the strong nuclear force. This is not the gluon field. This is the pion field. That's an effective field that's generated from those gluons. So let me go back real quick to what I had mentioned before. So you have a quark. Here are the 3, or I'm sorry, you have a proton. Here are the 3 quarks in the proton. You try to pull this quark away. So here's this quark out here that you have pulled away from the proton. So the proton is now this kind of stretched out thing. There's still going to be gluons interacting with everything. So there's gluons all over the place. The gluon field will spontaneously produce a quark anti-quark pair, and the quark will latch on to the previous 2 quarks, basically replacing the one that you're pulling out, and the anti-quark will couple up with that one. And so that gives you a proton. So you still have the proton left over, and you have this pion that comes out here. So the nuclear force, the strong nuclear force, fundamentally is these gluons interacting with the color charge. But on we'll call it a mesoscopic scale, on the scale of the nucleus of an atom, instead of a instead of a particle smaller than the nucleus, we're talking about on something the size of the nucleus, it's actually these pions that are exchanged, and not the gluons that are exchanged. So these pions are the things that actually bind the nucleus together. And so it's an effective force, kind of like the tension in a string is a force, but it's a force that comes from the electromagnetic bonds of all the chemicals in the string. And so when you pull on a string, yeah, the tension is a force that you're exerting, but fundamentally it's the electromagnetic force, just manifest on a macroscopic scale. The similar kind of things going on here. Fundamentally, it's a gluon force, the gluon field that's keeping the nucleus bound together. But on a macroscopic scale, which means in this case the size of the nucleus of an atom, which is subatomic still, you're actually producing these pions and exchanging pions in the nucleus, between nucleons in the nucleus. So between the protons and neutrons bouncing around are these pions. Okay, so the pion field is going to produce a potential that looks like this. Okay, and so it gets weaker as you go out to infinity, but it's very, very strong when you're close in. And so you can trap things down here. So here is the pion field that is produced by the presence of a proton. Or in this case, it's a neutron. We'll talk about protons in a minute. In this case, this is the pion field, the potential produced by a neutron. And so you bring something else in and it can bind to it. You bring another neutron in and it will stick to this neutron. You'll form a 2-neutron bond, like bound state. And there you go. That's what you get by having these two particles interact. If, on the other hand, you bring in a proton is a bit different because a proton also has electric charge. And when you do the combined strong nuclear force and the electric force, it doesn't just go to zero out here. What happens is it rises up first from the electromagnetic field, and then it drops down. So this is the potential you get from a neutral particle. This is the potential you get from an electrically charged particle. So this would be like the neutron, the potential from the neutron field, and this would be the potential from a proton field. So because this has the electromagnetic field, if you try to bring another charged particle, like another proton, into the mix, it will feel the electrostatic repulsion, right? It's going to try to work its way over this potential. It may not be able to, in which case it will reflect off of this for the same reasons that it would reflect off of something rolling up a hill that doesn't have enough energy to make it over the hill. So it'll make it up to some point and it will roll back down. And where that happens is related to the kinetic energy of this particle and then the potential energy that it has by moving around within this field. The neutron doesn't have this problem. The neutron doesn't feel the electric force or the electromagnetic force, and so the neutron will just come in and stick. Okay, so this is the interactions that will take a proton or a neutron and bind them together in a nucleus. It's the strong nuclear force that gives this highly attractive region. It's the electromagnetic force that gives you this repulsive region if you're electrically charged. Okay, so then what's going to happen? Well, you're going to bind these things together. The simplest nucleus of an atom is just a hydrogen atom, just a single proton. The next simplest one is deuterium with a neutron and a proton. A neutron, when it's left alone, doesn't live very long. It's not stable long term, and it will spontaneously decay after about 10 minutes. We will get into what those decay modes look like in a minute. Okay, so here is the nucleus. You start adding more protons to this nucleus, and you run into the following problem. If you're just adding protons to the nucleus, you run into the problem that all these protons are trying to also get away from each other. They're attracted to each other through the weak nuclear force, through the strong nuclear force, through this exchange of pions. But they're also repelled from each other because they all have the same electric charge. And so it's a positive electric charge and they're separated from each other, and so they're going to experience a force because this is going to be Q up here, and this is also going to be Q, and when you have the electric force, it's going to drive them apart. So the way that you keep the nucleus together is by adding to the mix a bunch of neutral particles that add glue to the system. They add more pions to the environment, so that increases the bonds between these different nucleons. But it doesn't increase the electromagnetic force. It's a way of adding more glue without adding more of the forces that are trying to pull the nucleus apart. So in order for a nucleus to be stable, you have to have a good mixture of protons and neutrons. So for the low mass stuff, the most stable mixtures are ones where the protons are equal to the neutrons. But this doesn't happen. This is only true for the most stable nuclei when the nuclei are small. As the nucleus gets bigger, you run into the following problem. The strong nuclear force is a short-range force, and the electromagnetic force is a long-range force. So here's the strong nuclear force here that only persists over a relatively small distance, where the electromagnetic force up here, whoops, not what I meant to do. The electromagnetic force up here, this extends for, out to infinity. So the electromagnetic force at some distance is always repulsive, and you might be lacking. So like this proton up here and this proton down here, they can feel each other's electromagnetic force that's driving them apart without feeling the attractive force that would keep them bound together, because this distance here, the distance over which the pion field can propagate, is really only to your nearest few neighbors. So the pion field will bind things together in a local environment. This local environment will be bound to the next local environment because they share neighbors. But the particle up here, even though it's only a few neighbors away, is not going to experience a strong bond to the proton on the opposite side of the nucleus. So as the nucleus gets larger, the protons, they're all going to be repelling each other, and as they get too far away from each other, there's no strong nuclear force anymore that binds them together. So now you've got a proton out here and another proton out here. The bonds that they share are the forces they experience from each other are only the electromagnetic force, and so they repel each other. So in order to keep the nucleus bound together, you eventually get to a situation where you have to add more neutrons than you get protons. So once the nucleus gets big enough, then you have neutrons being more than protons. So if we take a look at what are the stable nuclei that you can form, you get the following very famous representation. So stable isotopes. You get this plot right here. New tab. Oh, yay. Okay. You get this plot right here. Okay, so this shows a list of the stable nuclei. The stable ones are in black. Unstable ones are everything else, basically. This also tells you how they decay. We haven't gotten into what those decays look like, but it tells you how they decay. So the stable ones are the ones that are running up along the center. The number of protons is on the, in this case, is on the horizontal axis. Normally, when I look at this picture, I look at it flipped over. It would fit better on the screen if it was flipped over. Actually, let me see if I can find a flipped over version. That's not it. That's not it. No. Nothing's showing up here. Stable isotope plot. These are all tilted backwards. Okay, this is the one. Here we go. Here's one that's turned sideways. Okay, so it's exactly the same plot, except now it's flipped so that you have protons on the vertical axis starting at 0, and you have neutrons on the horizontal axis also starting at 0. And the stable nuclei are in black. So now you can fit the whole thing on there at once. So these are all the stable nuclei. They come up here. Notice that there are some, so the number of protons tells you what element you're speaking of. So if you're talking about carbon, then it's going to be down here. And some of these elements are going to have multiple stable isotopes. So for example, we know that carbon 14 is not stable, but carbon 13 probably is stable. So you can have a carbon 12 and a carbon 13. You can have iron. This is probably iron right here. Iron, I think, is 26. Maybe this is iron. So iron has multiple stable nuclei, and they all lie on roughly this line. Initially, this part of the line down here. Hold on, let me make my pointer a little bit bigger so that people can see it in all of its power and glory. But the small proton, so like the small nuclei, carbon, nitrogen, oxygen, things like that, those are all going to have equal numbers of protons and neutrons. When you get to the larger ones, like this big, you get to the larger ones up here, then you have to add more neutrons to the system. And so the initial line would come up at an angle like this, and the stable nuclei tend towards more neutrons than protons. So what does this imply? Well, some elements, some numbers here, there are a few of them, not very many, but there are a few numbers where there is no stable element, right? Remember a horizontal line corresponds to a given element because that's a fixed number of protons. So a fixed number of protons is a horizontal line. And you'll notice that like in this area right here, there's no black dots. There are no black dots at this location, which means that there are no stable elements, stable nuclei with an atomic number of, it looks like 61. We can check this to make sure, because that is probably technetium. So technetium is not stable. Technetium, that's 43. Okay, so that's not what I was thinking of. Let's see. Okay, so technetium is 43. Let's see if we can find 43 on this diagram here. 43, right there. That one's technetium right here. So there's nothing stable right there at that element. So technetium has no stable nuclei, which is a sad thing, but that's the way that it is. Up here, this is probably, maybe this is like radon or something like that. 60. 60. What do we have near 60? 54, 60. So we're looking at neodymium or promethium. It's probably something like promethium. So there's probably no stable elements of promethium. Neodymium probably is stable because it's an even number. It's typically the odd numbered ones that are not going to be as stable. So anyways, we get this area where we have these big floppy nuclei that aren't stable in nature, or at least on their own. And so that shows up as a gap in these things. Okay, so that is the types of elements that you can form. Each one of these, when you have a given number of protons, this is a given element, and all of the allowed number of neutrons in there correspond to the different isotopes. So carbon 12, carbon 13, carbon 14, nitrogen 14, nitrogen 15. All of these things are different isotopes of a given element. So those are the number of neutrons that you have in there that changes the mix of and what the internal workings are of the nucleus. A few things to note. When you add nucleons to the nucleus, you get a different nucleus. Okay, you have this collection of things. They're all bound together with the pion field, with this strong nuclear force. So these things are all bound together. If you add something else to that nucleus, it's a different nucleus. It is not the same nucleus. When you're looking at the periodic table, so this, not that periodic table, let's try this periodic table. Here, these elements in this periodic table, these are different chemical properties. This is organized by chemical property. This tells you about the number of electrons that you have in the system. It doesn't tell you about the number of neutrons that you have in the system. It's just how are the electrons arranged and how do those electrons interact with each other. That is not the nuclear force. The only reason that these electrons even exist around these nuclei is because one of the two nucleons, namely the protons, have electric charge and therefore can attract the electrons to them and bind them to them. If you didn't have the protons, then things would be different. So the electromagnetic force does play a role in the nucleus, but it's not the same role. It's not as strong role as having the different number of nucleons that are in there. So the neutrons and the total number of neutrons and protons. Neutrons and protons, they have different quantum numbers, and so they can't occupy the same space at the same time. And they interact with these pion fields slightly differently because some of the pions are charged as well. But nevertheless, they're effectively the same type of particle that are in here. When you add these things down, or when you add these things, a new nucleon to the nucleus, whether it's a proton or a neutron, you've actually changed the properties of the nucleus. The nucleus is no longer the same animal. The chemical element might be the same, but the chemical element is dictated, the way that the chemical element behaves is dictated by the electron field, or the electrons that are going around it. The electrons, of course, are selected by the protons, but that just is a happenstance. There happen to be 7 protons in the nucleus, and therefore you get 7 electrons going around it, and those 7 electrons behave a certain way, and therefore you get the chemical properties of, what is it, nitrogen? What is nitrogen 7? Yeah, so then you get the chemical properties of nitrogen. If you change the number of protons, then you change the number of electrons. So if I remove a proton, I'm going to get carbon because I have a different number of electrons, and carbon has the chemical properties of something that has 6 electrons. Here's a question. Why is it ordered by electrons and not by protons? Okay, so it's ordered by, well, the number of electrons is equal to the number of protons when you have a neutral atom. So if you don't have equal number of electrons and protons, then you have an ion of some sort. And you can have, triply ionized something. It's not just a single charge that's missing. You can have multiple charges that are missing. But it is ultimately the number of protons that dictates the number of electrons that you attract to your electron cloud. And so then you count it up by, then at that point, with a neutral atom, the number of protons and the number of electrons are the same, and so you order them basically the same way. The issue is that the structure of the periodic table, this structure that you see in the periodic table, I don't know what I went over there. This comes from the properties of the quantum states of the electrons. It's what shells are the you have the wave equation, you have to solve the wave equation in 3 dimensions with this potential in the middle. You have to match up the boundary conditions. If you go around the 2 different angles, you have to have the right number of nodes for the wave as it propagates inwards and outwards. And so the solutions to the wave equation give you the different electron orbitals, and then you have 2 spins for each electron orbital. And so that gets you this arrangement. So the periodic table is dictated by the properties of the electrons, and the chemical properties of the different elements are dictated by these electrons. And so it's a bit of a misunderstood situation that the nucleus doesn't really care what's going on with the chemistry. The nucleus doesn't care that you have sodium chloride. All that the nucleus cares about is the fact that it has some number of protons in the middle. Okay, and so one consequence of this is that people mistake uranium, for example, and I'll go into a bit more detail about this, but I pointed out uranium-235 and uranium-238, they're both uranium because they both have the chemical properties of uranium. They have the same number of electrons as uranium. But uranium-235 and uranium-238 are very different nuclei because there's three more nucleons in the nucleus between uranium-235 and 238. That would be like saying the difference between lead and gold, right? So lead is here. Where's lead? Lead is here, 82. It's got 82 electrons. If I go back 3, 81, 89, 70, or 81, 80, 79, that's gold. Gold and lead are as different from each other in their chemical properties as uranium-235 and uranium-238 are in their nuclear properties. So I explained in 10 to 15 minutes in something that took high school weeks to understand. So, well, I'm glad I could help out. So as you add these different nucleons into the nucleus, you're getting different animals. Even if they have the same number of protons, you're still getting different animals with different nuclear properties. And as a consequence, you're going to get different behaviors of those things. And some of the behaviors of these different nuclei are going to be related to how they decay and what happens to the nucleons that are within it. So you have this potential, or you have this energy that's associated with building these things up. So I add new stuff to the nucleus. Now I have a new energy state because you can't just add it for free. Or when you add something to it, you've changed the quantum properties of the nucleus. And so there is a binding energy associated with adding a new nucleon to the system. Basically, here's a way to think about it. Here's a particle out here. It's a very happy particle because it's free. So here's a free particle flying through space. Free particle is flying through space. Here is something down here that is also happy, but it only has one eyebrow, okay, like a star. So here's a star. I have this particle moving through space. It has some amount of energy, okay? It might interact with the star, but it's not going to be bound to the star. The only way for it to be bound to the star is if you can somehow give up energy out of the system and, in other words, remove energy from this object's motion and then couple it to the star such that it can go in orbit around it. If it's just passing by, it's not going to become bound to the star. You have to dissipate the energy somehow. Somehow you have to take energy from this original system, remove it from the original system, or put it in some other form to allow this object to bind itself to this star. So one way to do it would be to heat it up. Like you could change the shape of it, cause a lot of friction on the inside, heat it up, and then that transforms the bulk kinetic energy into thermal energy. But since you've removed bulk kinetic energy, the object is going to be moving slower and therefore can be bound. Another way to do it would be to have like some object here. As the free object comes in, it can kick out this other object, can exchange energy with it. This now carries energy out of the system and you become bound through that way. But the same thing happens with these with a nuclear process. When you're binding a neutron, say, to a proton, as these come together, you have to release some amount of energy. Somehow you have to get energy out of the system because otherwise they won't bind themselves to each other. In other words, you have to start, if we look at this thing again, so here's this well. If you're up here and you want to get stuck down at the bottom of the well, so here's now your two particles that are stuck in the bottom well. If you want to get stuck down there, you have to give up all this energy. Okay, and that energy is going to come off typically in the form of radiation, some form of radiation, in particular like a gamma ray. So as like the proton comes in and becomes bound, it will emit a photon with high energy. In particular, if it's just a proton and a neutron binding together, then the proton will emit a photon with an energy of 2 capital MeV, or at least you'll get 2 capital MeV worth of radiation that comes out of it. I believe it's a single gamma that comes out. So this is a lot. 2 MeV is 2 million times what it takes to ionize a typical atom. So 2 million times more energy as these things become bound to each other. and it gives off this energy, and that's what allows it to become bound. Otherwise, if it kept the same amount of energy, it would just go by, it would just drift by, and no problem. Where does this energy come from? Where does the energy come from to supply this gamma? The answer to that is the energy comes from the mass of these particles. You have this particle up here, it has some mass. Once it's bound in this state, the mass is less, and that the leftover mass, delta M, times c squared is the energy that gives off in this gamma. Now, fundamentally, it's a little bit more interesting than this, in that most of the mass of the proton, especially with a proton, it's not true with more massive hadrons, like a cascade particle or something like that. But the proton itself, most of the mass of the proton is actually not in the quarks. So again, if you look at the structure of the, oh, that's a heart. It's amazing. If you look at the structure of this, you have 3 quarks in here. Okay, each of these quarks has some mass. But the proton, if you look at the mass of the proton and you divide it up into parts, you get something like this. So this is the total mass of the proton, the mass of the proton. This is the mass of the quarks. Okay, the rest of this stuff is energy from the gluon field. So this is energy from the gluons. From gluons. And so the bulk of the mass of the proton is actually the mass of the gluons. So when you bind these things together, you don't even have to change the mass of the quarks. You change the gluon field. And you lessen the contribution to the mass from the gluon field, and that's what goes into forming this radiation. So that's pretty cool. All right, here's a question. Kicking out neutrinos or antineutrino particles. I haven't done the neutrinos yet, so that's a different type of decay, but we will get to that momentarily. Here's another question. Do I know if it's possible to work as a meteorologist or as an astronomer as a math major? You can work, I can't say much about meteorology as a math major, but I can say in astronomy, there are a lot of people who do math and then go into astronomy graduate school. So, I mean, it's not everybody, but it's enough that it's not uncommon. That counts as mass. Did I not learn that energy has mass? Yeah, well, energy, it's energy that couples to the gravitational field. It's for most macroscopic cases, or most cases that we confront, most of that energy is in the mass, is in the mc squared portion. And so it's a reasonable approximation to say that mass causes gravity. The reality, though, is that energy causes gravity. And that's what causes the distortion of space-time. And so the energy that goes into the bonds inside the nucleus from the quarks contributes to the total energy of that system. So let me see if I can find a figure that shows the mass of the proton versus mass of quarks and gluons. I know I've seen a picture that shows this. I just don't know if I can find it again. Pie chart of the proton mass. Let's try this one. Pie chart of the proton mass. Make me proud. So the quark mass is like 10%. Weird. The quark mass, the mass of the quarks, because they do have mass, is only 10% of the mass of the proton. The energy of the quarks, that's their motion within this thing, the energy of the quarks is a third of the mass. The QCD trace anomaly, I'm not sure what the trace anomaly is, so that's probably related to the coupling of the gluon field with itself, maybe something like that. So that's going to be a quarter of the mass, and then another third of the mass is the energy of the gluon field. So this is probably something like the potential and the kinetic energy of the gluon field. And then you have the kinetic energy of the quarks, and you have the bare mass of the quarks. So that's my guess for what these two things are. I don't know that for sure, but either way, the point being that the mass of the proton is actually made up of, it contains all of these different sources of energy. So there are other places to give up energy. When the mass of the nucleons binds together, you lose some of that mass in the form of radiation, but that mass itself is coming from a variety of sources. Okay, where do we go from here? So that tells us, so now these things are bound together. When you keep adding nucleons to the mix, you keep giving up some of this energy, and you're forming something, this collection of quarks and gluons that are bound together in protons and neutrons that are communicating with each other by exchanging pions. That's the nature of the nucleus. As you add more stuff, you change the nature of some of those interactions. You have a certain number of quantum states because each of these particles is a fermion, meaning that it can only occupy one quantum state. Only one particle can occupy one quantum state. And so when you add a new thing to the mix, you add it into a different quantum state. So now the quantum states are different. And so the behavior of the particle is going to be different. The behavior of the nucleus is going to be different. If you have too many of a type of particle, let me put it this way. There's going to be some optimum mixture of protons and neutrons. Let's say that you want a total number of protons and neutrons to equal, I don't know, like 100 or 50. As I said, anyway, so you want the total number of protons and neutrons to be 50. This could mean you have 1 proton and 49 neutrons, or it could mean the opposite, 1 neutron and 49 protons, or even 50 neutrons and no protons, and everywhere in between. And so the question is, which one of these is the most tightly bound? Which one of them has the most favorable, or which one has given up the most amount of energy? That's going to be that's the most tightly bound nucleus, the one with the strongest interactions between everything that's in there. So when you look at the binding energy that you get for this mixture, it's going to be fairly small. And for this mixture, it's also going to be, well, maybe the way to say it is, it's going to be very large. Okay, so binding energy is usually negative. So we'll say that the favorability is small for these ones, and you get more and more favorable as you mix them up in different ratios. So maybe like 15 to what? 25? So maybe the 15 to 25 mixture of protons to neutron, that's going to be more tightly bound than the 1 to 49 mixture. And maybe it turns out that it's the 18 to 22 mixture that is the most tightly bound. Like this is the most energetically favorable combination of protons and neutrons. Okay. Part of the reason for why this would be the case is because the protons are slightly less massive. Protons are slightly less massive, but they also have electric charge, and so they contribute a little bit to this electromagnetic field that you're generating in the center. Okay, if this is the most tightly bound nucleus, that's going to be the one that's most stable. So if you are a nucleus that's sitting out here that looks like this, so you're a collection of neutrons and protons with 50 particles in it that is out of balance or displaced from the minimum, then what will happen is that some of these will spontaneously transform. So some of these neutrons will spontaneously transform into protons until you come into equilibrium. The way that they do that, oh, this is 40. You're right, that's 40. So this would be a 32. This one's 40 as well. How about if I do my math correctly? So that would be a 35. And instead of 18, let's go with 28. 28, and we'll do 22 and 28. So this would be a 35. One can add. This will be a 22 and a 28. Okay. If this one's more energetically favorable, then what will happen is you will start converting the neutrons over and turning them into protons over time. When I say most energetically favorable, what I'm talking about is when you look at the amount of binding energy, you have a surface, and typically it's plotted this way. So this is the energy released in the bond, energy released when the bond forms. And so this is going to be the proton to neutron ratio, basically, in this direction. And when you have all protons, you're up here, and this is the amount of energy that's released when the bond forms. And so if you start changing the composition, you're going to move along this until you get down to the bottom where you have the most energy that's given off as that bond forms. And then the same thing as you come over here, it's going to get less and less energetically favorable, meaning that your nucleus is less tightly bound. If it's less tightly bound, it's easier to break apart, right? A less tightly bound planet is going to be way out in the distance and easier to strip off of a star. A more tightly bound planet is going to be closer to the star and is therefore harder to remove from that system if you want to ionize a planetary system. Okay, so you want to find this optimum ratio. Now, this always comes in integers, right? Protons and neutrons always come in integers. And so you can't necessarily be right at the bottom of this curve. Well, okay, so the curve is made up of the points, and so there's definitely a bottom. But there's if you smooth out or you do some kind of interpolation between all those points, you may not necessarily land at the bottom of where that interpolation would tell you, because all you can do is move one over, like one place over and one place over and one place over from there. So anyways, you will settle, the system will work its way down towards the bottom of this trough in the binding energy that you get. If you're too far away, then you're going to do, in this case, if you're too far away where you have too many protons, well, so I'll call this too many protons, and this one is too many neutrons, then you will either spontaneously absorb, if you have too many protons and you have these electrons that are out in the shell, you'll either spontaneously absorb one of those electrons, that's called inverse beta decay, or you'll absorb a positron from the electromagnetic field, or not from the electromagnetic field, but from the electron field. And then that will convert you into a neutron and you will skip down like this. And maybe you'll do it twice. So you do 2 beta emissions and then get down here to the bottom, where now there's no particular, there isn't enough energy that you would gain by going through a kind of a complicated process. If you have too many neutrons, then you will spontaneously emit an electron, and that will turn the neutron into a proton. You'll emit an electron plus a few other particles, but we won't be talking. Well, okay, so you emit an electron and a neutrino, an antineutrino. The details of that interaction is for a later chapter. And you will now change that neutron into a proton, and that will advance you in this direction until eventually you settle down here. That's what shows up in this figure. Where is it? This one. So when it says a beta plus emission, so decay modes beta plus, so that is either you emit a beta plus, you emit a positron, or you electron capture. Okay, that's where you steal an electron from the environment. This beta minus, which is over here, beta minus is where you actually emit an electron. So the neutron will spontaneously emit a neutrino and an electron, and that electron leaves the system or becomes bound to the electron shell. But this is, notice that this is too many neutrons. So we're talking about a given number of fixed things, which will be a slice. So a fixed number of nucleons will be a diagonal slice. So you have a diagonal slice like this. That's the fixed sum of protons and neutrons. And so if you're down here, then that implies that you have too many neutrons. And so you will decay diagonally up and to the left until you land on this, on a stable element. If, on the other hand, you have too many protons, then that will put you up on this side of the of this valley, and you will emit, or you will absorb, you'll capture an electron, or you'll emit a positron, and that will drive you diagonally down this way until you hit a stable isotope. Okay, let's take a look at there is actually a plot that shows what these binding energies are, and that's called the Valley of Stability. Here we go, ready. Valley of Stability. Let's see if I can show. Yeah, this one's good enough. Okay, so this is an interesting way of representing it. Is there one that's higher resolution? Doesn't appear to be. Okay, that's definitely lower resolution. So we'll use this one. So here is the Valley of Stability. When you have too many protons on this side, so this is reversed from the way that I showed it. We're looking this way. We're looking one direction up the valley. The other way, we're looking down the opposite direction of the valley. Too many neutrons are up here. Too many protons are up here, and so you will emit and slide down the drip line. So that's the direction that you move. You'll start here. You'll move diagonally down until you reach a stable element. Okay, here's a question. What happens to the technetium when it decays since it doesn't have a stable black dot? So the technetium, let's take a look at technetium. We can probably do that. I'll pull up another thing. So technetium, I think I probably spelled that wrong. I probably even saying it wrong, but yeah, that's okay. We'll look at the decay modes. The decay modes should be given here. Somewhere should be given here. I think it has a fairly long half-life. Okay, here's the different technetium isotopes. The abundance, this sin is synthetic. This trace means that it actually does occur naturally, but it's very, very short. Well, it's short-lived relative to the age of the solar system. So this Technetium-99 has a half-life of 10 to the 5 years. So that's 200,000 years. Here is one that has an isotope that is 4 million years. Probably the reason that we don't see this one is that the way that you would produce this isotope, there's no natural way to produce this isotope. My suspicion is that there is a natural way to produce Technetium-99, probably from the decay of some other particle. You have some particle, it's going to spontaneously decay through some mechanism that we haven't gone over yet, and it will eventually produce Technetium-99. Also, Technetium-99 you produce in nuclear fission reactors. But anyways, it has this half-life. It emits through beta emission and turns into rutherfordium 99. It's through beta minus. This one here, 98, it also decays through beta minus emission to rutherfordium 98. Ruthenium. I apologize. It's not rutherfordium. Ruthenium. You can tell I'm not a chemist. And then, so some of these other things. This Epsilon emission is, what is that? I don't remember what the Epsilon emission is. Electron capture. So this Epsilon is electron capture. So this technetium does it through electron capture to move its way down to a different element with a different combination. So what that probably implies is if you were to look at the valley of stability right around that technetium, it would probably have something like this, where you have the different isotopes of technetium are like this in the valley, and then you have a ruthenium. So here's the valley, kind of like that. And you probably have a ruthenium down here. And so since these two technetium isotopes are kind of displaced from the floor of the valley, that is just viewed as energetically favorable to move your way here or up here, instead of, because there's no isotope that you can make that sits at the bottom. So that's why it would be unstable, is that you're far enough on the sides here. Here are the different isotopes that you get for technetium. They live on this curve. And it's downhill to go either up or down this valley. So the valley does have a slope. It's just that it's more downhill to go. Even if you go up the valley instead of down the valley, it's more energetically favorable to do that. And there's no combination, there's no integer number of protons and neutrons that will set you at the bottom of the valley. So that's how this would look in that diagram. Is that why I make fun of chemists? I make fun of chemists because that's how I feel good about myself. If I didn't have chemists to make fun of, then I would be like, I'm just a poor boy from a poor family. Here's a question. How are half-lives related to radioactive nucleus stability? So the more stable the nucleus is, thank you for that sub, the more stable the nucleus is, the longer the half-life will be. So a long half-life corresponds to a more stable nucleus. If you have something that has, and something else to consider, because this always comes up when people talk about nuclear energy, is that the longer the half-life is, the more safe it is to hold in your hand. Not that you should be holding radioactive sources in your hand, but the longer the half-life is, the more stable the nucleus is, the smaller the rate of decay, the smaller the amount of the smaller the amount of nuclear radiation you get. If there were no laughter, there would be no chemistry. So when you have things that are very unstable, then they decay rapidly, and you get a larger dose of radiation. So less radioactive is more stable, longer half-life. Sometimes people say, this has a really long half-life, therefore it's dangerous for a longer period of time. And that's not exactly, it's not an accurate description of what's happening. There's some nuance there to consider, and that is, the question is, what is the rate of decay particles that are coming out? And the longer the half-life, the slower that rate. Okay, so that's technetium, and this is the valley of stability. Here's a question. I'm curious. When did they figure out about atomic number Z? During Mendelev's time, they surely had relative weights between the elements and hydrogen. Well, I guess the question is, when was the proton discovered? And that's a great question, actually. Who discovered the proton? Was it Chadwick? Or did he discover the neutron? Discovery of the proton. So Rutherford Rutherford discovered the nucleus. I guess maybe that counts as the proton as well. So Rutherford did the gold foil experiment where he had a thing of gold foil here. He had a source that would produce alpha particles. This was before they knew what alpha particles were. The alpha particles would stream over and hit this foil, and most of them would deflect a little bit, but then some of them would bounce backwards. The only way for the alpha particle to bounce backwards was if the electric charge in the nucleus was highly concentrated. And so at the time, the model for the atom was that you had the plum pudding model where the electrons were embedded in a larger substance. So it was like a boule de glace avec des noisettes in there. And so the prediction was that the alpha particles would come in. They knew that alpha particles were charged because you can just put them in an electric field and measure what the charge is and the mass. So the alpha particles would come in, they would interact with this collection of charges, and then they would deflect by some small amount. However, if you have all of the electric charge, positive electric charge concentrated in the nucleus, so here's all your electric charge, and then you have this fluffy atom out here, then you can get situations where the alpha particle comes in and then bounces off like that. And that's what he observed. And so that demonstrated that the nucleus was actually physically distinct from the electrons. And it was highly concentrated mass and electric charge. Okay, so does that count as the discovery of the proton? Perhaps. The neutron, I think, was discovered by Chadwick. Discovery of the neutron. I'm not totally sure how this was done. By 1920, physicists knew that most of the mass at the center of the atom was located in the nucleus. The core contained protons. In May 1932, James Chadwick announced that the core also contained a new uncharged particle, which he called le neutron. What did he... this was a lot of stuff. A lot of stuff was done in the 1930s, right? This is 1932. I think it was 1937 or 1938 when fission was discovered by Lee Smitner and Otto Hahn. And then they smuggled Mittner out of Germany. So it was right when they started taking the passports away from the Jews in Germany. So the 1930s was basically when most of this science was done, from the 1920s through the end of the 1930s, because then the bomb was in the 1940s. Okay, how did this, in 1914, he decided to travel to Germany to study with Hans Geiger from the Geiger counter fame. I'm not totally sure how the neutron was discovered. Hitting the paraffin target must be high energy gamma photons. Chadwick thought that the explanation didn't fit. Photons having no mass wouldn't knock those loose particles as heavy as protons from the target. He reasoned. Okay, here's the experiment. One experiment in particular caught his attention. Okay, Wikipedia page for the proton has a history section. Apparently some guy called Antonius van de Broek figured out Z. Did I have that one on here? I apologize for this distraction, but it's important that we get the history right. So discovery, proton, like that, from Wikipedia. So Z is just the number, the atomic number. History. Where's this guy? Antonius. Following the discovery of the atomic nucleus by Rutherford in 1911, Antonius van den Broek proposed that the place of each element in the periodic table, its atomic number, is equal to its nuclear charge. This was confirmed by Moseley in 1913 with X-ray spectra. Okay, so that's how this was able to tie to basically, so the periodic table up to this point existed, but it existed because of the properties of the electron. And here he's saying, now we can show that the periodic table is actually a function of the charge of the nucleus. So that was an important incremental step in kind of piecing together the atomic theory. Okay, so what did this have to do with, so the paraffin wax, he has these particles. One experiment in particular caught his attention. Frederick and Irene Joliot-Curie. Frederic and Irene Joliot-Curie had studied the then unidentified radiation from beryllium as it hit a paraffin wax target. They found that this radiation knocked loose protons from hydrogen atoms in that target. So wax has a lot of, it's hydrocarbons, right? Wax is made out of hydrogen and carbon. It's like oil. And so it has a lot of hydrogen atoms and it has a lot of carbon atoms in it. And so hydrogen atoms, if you're going to bombard this target with some of these radiation from beryllium, which would have been alpha particles, probably, because those are the ones that are going to make it into the nucleus, then those alpha particles are going to come in and they're going to knock particles out, usually particles of similar mass to the alpha particles or smaller, which would be protons. Radiation knocked those protons from the hydrogen atoms in that target, and those protons recoiled with very high velocity. Joliot-Curie believed the radiation hitting the paraffin target must be high-energy gamma photons, but Chadwick thought that the explanation didn't fit. Having no mass, photons having no mass wouldn't knock loose particles as heavy as protons. Okay, so this beryllium, the beryllium radiation that's coming out was actually probably, I'm wondering, well, anyway, so let's keep going. Instead of me making stuff up, let's just see what it says. He tried similar experiments himself and became convinced that the radiation ejected by the beryllium was in fact a neutral particle with the mass of a proton. Okay, so the beryllium is decaying by emitting a neutron. He also tried other targets to the paraffin wax, including helium, nitrogen, and lithium, which helped him determine that the mass of the new particle was slightly more than the mass of the proton. Chadwick noted that because the neutrons had no charge, they penetrated deeper into the target than a proton would. If you send a proton in, the proton's going to come in and it's going to recoil off of the charge in the nucleus because you have electromagnetic forces and they're going to repel each other. So unless it comes in with a lot of energy, you're not going to be able to bind them together. In other words, if you're not going to be able to bring them in with energies approaching the core of the sun, the energy at the core of the sun, then you're not going to get fusion to take place. But if you're sending in a neutral particle, there's no electrostatic repulsion, and so it's going to just come in and bind itself to the nucleus. And so February 1932, for 2 weeks of experimentation, imagine that. Imagine today, you have 2 weeks worth of experimentation and you discover one of the most fundamental particles in the universe. That would be gnarly. Published a paper entitled The Possible Existence of a Neutron, which he proposed the evidence favored the neutron rather than gamma ray photons as the correct interpretation of this radiation. So you have this source, it's emitting some kind of radiation, and he put it up against a wax target. It was knocking out protons from that wax target, which implies that it's something of similar mass to the proton that's going through. So that's pretty cool. That was how the discovery of the neutron took place. All right, so this gets us to those types of emissions. Where we're looking at here. Yeah. So this is beta emission, to go diagonally, switching one proton for a neutron or one neutron for a proton, depending on the type of beta emission you're talking about, whether it's absorbing an electron or emitting an electron. So beta emission is the absorption or emission of an electron, or the emission of a positron. And it will preserve the total number of nucleons and just move you in a diagonal fashion. There are other types of radiation that you can emit, and that is given by, you can see all of these yellow points. So the yellow points is when you have so let's do a plot here. Okay, here's a graph. This graph shows like the number of protons, so like 10, 11, 12 protons, 13, something like that. And then this will be 10, 11, 12, 13, and this will be neutrons. And so your stable stuff is going to be, for example, here or here. If you're converting a proton directly to a neutron through beta emission, you're going to be moving diagonally like this, or diagonally like that, or diagonally like this. So that moves you diagonally. But it doesn't move you down or up this valley. And so there are some places in the valley where it's energetically favorable to move down or up that valley, based upon what are the binding energies of nearby nuclei. So the only way to do that would be to actually remove particles from the nucleus. So you could remove a neutron, you could remove a proton. Neutrons are going to be easier to remove than protons. I mean, that's how Chadwick discovered them. Is that true, that neutrons are going to be easier to remove than protons? Well, anyway, so neutron, you can emit a neutron, or you could emit some collection of protons and neutrons. And it turns out that if you emit 2 protons and 2 neutrons, this is apparently energetically a very reliable way to do it. 2 protons and 2 neutrons simultaneously. So this is basically helium. You're emitting helium out of the nucleus. You're spitting out a helium nucleus. And what does that do? Well, that moves you 2 protons and 2 neutrons down. So you move diagonally 2 in this direction, and you've lost 2 protons and 2 neutrons, or 2 neutrons and 2 protons, right? It's the same. So you move diagonally down like this. When you're done, as you're navigating this valley, maybe emitting 2 protons and 2 neutrons still puts you in a position where you're energetically unfavorable and you require an additional beta emission or even an additional alpha emission. So this is called an alpha particle. So alpha emission is that you're moving down the valley of stability 2 squares at a time, kind of like is it the elephant? In the original chess game, or one of the early chess games, there was a piece called the elephant that could attack diagonally 2 squares, kind of like the inverse of the knight. Because knights in chess have a hard time attacking twice diagonally, but this elephant would do it. Anyway, they got rid of the elephant, but anyways. So this is alpha emission. So if we look back at this landscape here, alpha emission is going to take something from this area and move it directly diagonally down like this. And notice that because of the shape of this curve, if you move directly diagonally, this is a shallower slope than diagonal, and so it will move you diagonally down towards this valley of stability again. So you start here, you're going to emit alpha, maybe you're going to do alpha and then beta. You know, as you move diagonally, it's going to put you into some other space here where you may still get a chain or another sequence of radioactive emissions, whether it's through beta emission or an additional alpha emission. Okay, so there you go. That is another way to produce a more stable nucleus, is to basically just change the total number. So you'll notice up here in this area that there are no stable nuclei. None of these nuclei are stable. So if you look, for example, 92, element 92 is uranium. There are a number of long-lived half-life elements up here. So there's a number of things that live for a long time, but there's nothing that's stable. And so for a lot of these things, you'll get alpha emission, several alpha emissions to bring you down into here, and then you may get a beta emission or 2 that eventually drives you to this one right there. So that number of protons. That number of protons is 80, is it 80 exactly? I'll be able to tell you by switching to the periodic table. It is 82. 82. So lead is stable. And so a lot of these high mass elements will decay through alpha emission down to 82 to lead, which is, I believe, the most massive stable nucleus that we have. Some of them can live for a long time, but lead lives forever, as far as we can tell. We've never seen it decay. Okay, we can see down here, way down here, that you can get these. So neutron emission is the pink. So here's neutron emission. And so this element right way down here in the corner, that's probably the beryllium decay that was used by Chadwick. You can also see some places where you get proton emission, the red. Not very many of those, but you do get some, where you'll just directly emit a proton. And that also changes the number of particles, the total number of nucleons. Where beta emission does not. So there we go. That's 2 of the decay modes that you get. So we've talked about the nucleus and how you have 2 different decay modes. You have beta emission, which is either an electron that you emit, or it could be a positron that you emit, so that beta plus emission, or you can capture an electron, and that will ultimately, hold on, I gotta move my leg. That will ultimately result in a positron emission. So beta emission is you're switching from a proton to a neutron or vice versa and emitting or absorbing an electron. And these are the particles that come out, beta emission. There's alpha emission, which is helium-4. It's basically a helium nucleus that comes out. And there you're actually changing the total count of electrons and protons. This typically comes from massive objects. This comes from intermediate mass objects that are just off of the floor of the valley of stability. There's one other form of radiation that is emitted by nuclei, and that's what happens when you bring a nucleon in. So like here's your nucleus right here, and you bring another nucleon in, but it gets put into an excited shell, an excited state in the nucleus. Similar to having an electron, you bind an electron to an atom, but it's up in an excited state to start with, and not in the ground state. So if you have this, say, a proton that's up here in an excited state, it's going to spontaneously move down into its ground state, like what the lowest energy state available to it. When it does that, it's going to emit a photon, okay, because it's a charged particle. It's going to emit a photon. When it emits a photon, this is, well, the chemical symbol for photon is gamma. So gamma emission is this, what happens when the nucleus, you form a nucleus, it's in an excited state, an excited quantum state, and then it will, the nucleons will rearrange themselves, preserving the number of nucleons that you have. So you still have the same number of protons and neutrons. It will rearrange itself, and it will emit photons as that energy gets released. So gamma emission is another form of radioactive decay, but it's not a radioactive decay that actually changes the chemical composition. So whenever you emit an alpha particle, you're actually changing the element. You're changing the number of protons in the nucleus. When you emit a beta particle or absorb a beta particle, you're changing the numbers of protons and neutrons in the nucleus, which means that you're changing the chemical that you have, that you're working with you. The nucleus change is relatively minor, right? I'm just switching a proton for a neutron. But the chemical effect of that is that now you have a different number of electrons, and so you have a different electron cloud, and so you get different chemical bonds that form. Gamma emission doesn't change the number of protons, and therefore doesn't change the element at all. And so, so there's that. Let's see. If I recall correctly, lead concentration was used to figure out the age of the Earth. Yeah, that's probably true, because lead, the amount of lead compared to the amount of uranium tells you how much uranium you started with, and then how much of that converted into lead is one way to do it. Okay, have I, so those are the different forms of radiation, beta, alpha, well, alpha, beta, and gamma. Let me see if there's something else that I should be talking about. We did binding energy. Nuclear decay and conservation laws, like, so the number of electric charges has to be conserved in all these decays and stuff like that. We've done some substructure of the nucleus. When you put these things in there, they're going to have the same, they have to satisfy the same quantum behavior. They still have to satisfy Schrodinger's equation. And so you're going to get the same kinds of neutron and proton orbitals that you would get when you have electron orbitals. And so you're going to get effectively a chemistry of the nucleus, meaning the quantum states of the particles in the nucleus. And when those things, when those particles in the nucleus flop around, you're actually changing, you can change from one chemical element into another because you have a different number of protons now, which means you're going to have a different number of electrons bound to that. Okay, the last thing is about tunneling. In the core of the sun goes through nuclear processes to shine. It has this thing where you've got a proton in here, which means you have both the electromagnetic force that's repulsive for like charges, and you have the nuclear force, which is attractive. The sun is actually not able to, doesn't have enough kinetic energy of the protons to bring them in and have them go directly into here, to get up over this hill. And instead what you get is a quantum tunneling, where it comes up here and it works its way through this barrier, has some probability of appearing on the opposite side of the barrier, and then it can be trapped. Then it emits its energy and becomes trapped in the nucleus. So this is how the sun shines. The sun shines because of quantum tunneling. So I guess I'll give a brief description of what quantum tunneling is like, and then we'll wrap things up. So when you have a wave function, so here's your wave function, you're talking about the probability of a particle being at a given location. The amplitude of this wave is related to the probability. So here is your wave function. It satisfies the wave equation. So you have a wave that's coming in like this. This wave has some wavelength associated with it. It's got some frequency associated with it. Okay. Anyway, so it's got the wavelength and the frequency associated with it. And this is the wave equation. The amplitude that you have here, the amplitude and the frequency are related to the relationship between the potential energy and the kinetic energy of your particle. Oh, so the book that I'm using here, it's openstacks.org. Okay, so the frequency that this is oscillating with is related to the kinetic and the potential energy. If you change the potential energy in the system, what ends up happening is that the particle slows down, you have less kinetic energy, and the wavelength, you end up with higher probability of being found in that location. So the properties of this wave function are related to, like how this wave function propagates, are related to the potential and the kinetic energy of the particle. And so you have some potential, like say you have a potential well that looks like this, the particle is going to have a higher probability of existing over here than it does existing over here. Because particles, when you go up in potential, they slow down. And so the probability of measuring the moon, for example, is more often farther away from the Earth than it is closer, because it's moving more slowly when it's up there. So anyways, the interplay between the kinetic and the potential energy tell you about like what the wavelength is and what the amplitude is and the frequency and so forth. So what happens when you come to a barrier? Let's say that you have some barrier that looks like this, and you have a quantum wave function that's moving along in this direction. It's going to hit this barrier. If the kinetic energy of the particle is less than the potential energy of the barrier, like the height of the barrier, you would think that, like classically, it will just bounce off. So here the particle is bouncing off of this. But what's really going on is that you have this frequency here. You know, this is given by some sine function that looks like this. When you cross this barrier, this frequency here is related to the square root of the, what I guess it's the kinetic energy minus the potential energy. Okay, so here's this thing, the frequency of its oscillation is related to this difference, the square root of that difference. I don't remember exactly what the function is, but something like that. And then once you reach a point where the potential energy is actually larger than the kinetic energy, then this quantity becomes negative. The quantity underneath the radical becomes negative. That means that it's I, right? You're getting an imaginary number. So it's I times the square root of some quantity. Well, now I take this imaginary quantity. Imaginary numbers are actually real. I mean, they exist because it's a mathematical structure. It's not like, anyway, so you have this complex quantity and you substitute that in for omega. Well, it turns out you may recall from your high school trigonometry that there's this expression e to the I theta is cosine theta plus I sine theta. Okay, so this is a trigonometric identity that's some guy that they named it after. Well, you can, so just take this here. Now I'm going to take theta and I'm going to change it to I theta. And so I put I theta in here. So now I've got sine of I theta, I cosine of I theta. Well, that's going to be putting an I up here. That's going to be e to the I times I theta. Well, I times I, that's I squared, that's -1. And I get e to the minus theta. So what's going on here? Once you cross this boundary where the potential energy, in order to get through it, the potential energy is going to be bigger than the kinetic energy that you have. This thing switches sign. That changes the quantum mechanical phase or something like that into a complex number. And that changes an oscillatory function into an exponentially decaying function. And so you get an exponential decay of the amplitude. The amplitude is the square root of the probability. So the probability is the square of the amplitude of this wave function. So the probability of detecting this particle decays exponentially in the interior of this barrier, but it doesn't go to zero immediately. It doesn't drop immediately. Now, if this went up to infinity, it would drop to zero immediately, but nothing ever goes all the way to infinity. So this comes up to this height. You have some finite potential energy to get over it, which means that you're going to have some complex number in here, and you're going to get an exponential decay of the amplitude, which means an exponential decay, the square of the amplitude is going to be 2 theta, so you get, anyway, still exponential decay of the probability like that. But it doesn't go to zero immediately, which means that there's some non-zero probability by the time you get to the far side of the barrier. It might be a small probability, but it's non-zero. Once you reach the far side of the barrier, now all of a sudden, the potential and the kinetic energy switch signs again, that difference switches signs again, and now you have some of the wave on the far side. That means you have some probability of a quantum particle tunneling through a barrier that it shouldn't otherwise be able to tunnel through, tunnels through the barrier, and then appears on the other side. This is how the sun shines. The sun shines by saying, here is the barrier that I have to overcome in the nucleus. I send a proton in. The proton doesn't have enough kinetic energy to make it over that thing, but the proton has a wave function. When that hits this barrier, then that probability is going to decay exponentially, but it doesn't go all the way to 0, right? 0 is going to be here. Doesn't go all the way to 0, comes out here, and then I have this probability on this side. And so that probability is going to be something like 0.000001. That's too many zeros, 1. So it's like 10 to the minus 6. So the probability of a typical proton in the core of the sun binding into a nucleus, or binding into with another proton in the core of the sun, is about 1 per million. In other words, it takes 1 million tries. You have to smash these things together 1 million times in order to get them to stick, something like that. And so how do you do that? Well, if you have them all concentrated in a high density region, then you can get 1 million collisions fairly frequently. But if you have a low density gas, then 1 million collisions is rare. Like each collision is rare, and so 1 million collisions is really small. So for the case of the sun shines not because it has enough energy to knock these, or to smash these things together to where they stick, but it has enough energy and enough density so that the number of times that it fails is, it doesn't fail so many times that it gives up. It's able to do it several, 1 million times a piece until eventually it works, and then you stick it together and you release that energy, and then the sun shines. If you were to try nuclear fusion on the Earth, where you cannot reach the same densities that you have in the core of the sun, then you have to do one of two things. You have to, you have one recourse left. If you can't reach the densities in the core of the sun, then you're left with needing to raise the temperature, the kinetic energy of the particles coming in, so that they can make it over in a single collision. So the temperatures that you have to have at, like, in a nuclear fusion reactor on the Earth is much higher than the temperatures that you need to have in a nuclear fusion reaction in the core of the sun. The core of the sun, it can operate at a lower temperature because it has a higher density and therefore has more trials, more collisions. For something happening in a nuclear plant, some future nuclear fusion power plant on the Earth, you have to raise the temperature higher than the core of the sun. Higher than the core of the sun means really hot. And so that dictates how you design your tokamak. Like, what do you use to confine these particles? Because when they're moving at high energies, they're moving at high velocities. They would escape your reactor very quickly if you don't have some way to contain them. So for the case of a tokamak, you have a large magnetic field that does it. Or you can confine them in these little beads so that you get the collisions to happen while they're still trapped in those beads. And so there's a variety of different ways to do that, something that we'll talk about in the future. But there you go. That's nuclear decay. We haven't done half-life yet. We'll talk about that. I guess that's part of the next chapter. But that's what the different nuclear decays are, and that's why the system decays. That's why nuclear particles, like nuclear elements, that's why the nucleus will decay into other elements, is because it's trying to find the optimum mixture of protons to neutrons that maximizes the binding energy, or maximizes the amount of energy that's been released in forming the bonds. There we go. Any questions on this? I appreciate the subs. I appreciate, hope that this was worth your while. Hope we don't need why does the sun really shine a few years from now. Do I allow viewing of the VODs? Yes, you can view the VODs all you want. I do actually take the VODs, minus the introductory stuff, but I do take the VODs and I post them to YouTube as well. I don't know, I get like viewer, maybe 2 viewers for them, but yeah, VODs are totally fine. Thank you, I appreciate that. So I do have a YouTube channel where I'm posting these things and some other things. Sun shines because he eats Raisin Bran and wears glasses. That's exactly what it is. All right, thanks a lot, everybody. I will be back on Tuesday. I won't be updating my operating system on Tuesday, so that will be good. Didn't there used to be an element that people thought had an infinite half-life, but it was discovered be incredibly long? That